Hello and welcome to lecture 6. In this lecture we're going to dive into the code and see how the concepts that we discussed last lecture are actually implemented in the code. So this is basically the same code we saw in prior lectures. The two main changes are I commented out torch.compile and I've added a breakpoint. So if we run this, we'll see that we breakpoint here. And I'm not going to step through all the code. I've actually instrumented breakpoints in the most important parts. But if interested, I'm happy to do another video where I show how I generally will step through their code to add these breakpoints. For the sake of time, let's just jump straight to the interesting parts. So whenever you do a DTensor operation, it will go through this opdispatcher dispatch method. And in this method, the most interesting line is this, which is a self.sharding propagator.propagate. This will do kind of the input placement resharding that we talked about last lecture. So if we come here, we jump down here, it calls this propagate method. And this is just some code to figure out whether or not we should cache it. For the first time, they will both end up hitting this method. And the most interesting part about this method is the following, where we basically will run the strategy propagation generation. At this point, it'll be interesting to inspect some of the state. So if we look at what op schema is, we can see that an op schema has a arg spec. And this arg spec basically tells us the input DTensors and their sharding placements. So you can see here that both tensors are sharded by column on dimension 1. And then the op is a A10 matmul. And you can see we're using the op to index into this op strategy func_dict to find the function we'll use to do the sharding propagation. And so if we run this, we see that we get here. And indeed, this strategy was registered to this a10.mm.default op. And that's why we landed here. And we call this a function like strategy, where we pass in this interesting looking string. This string is called an einsum string, and we'll quickly see why it's useful. So we'll come down to this like strategy, and this is where the magic happens. This is where we take the einsum string and we generate all the candidates for the input shardings. So if we jump in here, let's print out some code, some state. So print out the equation. This is the equation that we saw earlier. If we step, we see that einsum has figured out that the input dims are mk and kn, and the output dims are mn. And if we pass that into parse dims, then we'll derive this edims, einsum dims object, which will tell us all the batch dimensions, the contracting dimensions, and the left-hand side, right-hand side dimensions. And we'll use these dimensions to basically come up with candidates for sharding placements. Here we allocate a list, strategies over one mesh dim, which will basically aggregate all of the candidates as we go through. The very first candidate that we will always place in our candidates list is the replicated candidate. And the basic idea here is we just take all of our inputs and we replicate them, and then the output result will be replicated as well. And one thing to note is that these placement lists have like an implicit structure where we always put the placement of the output first, followed by the first input, followed by the second input. So that's the reason why we'll have length of inputs plus 1 times replicate to get the placement list for the replicate candidate. We don't have any batch dims in this example, so we'll skip over this. We do have a contracting dim, k is our contracting dim, and you'll see here that the placement list sets the output as partial, and then it sets the inputs as shard. And if we run this line, we can see that the placement list here, the candidate, looks awfully similar, awfully familiar. The output is partial. The first input is sharded by column, and the second input is sharded by row. And this is actually precisely the example we walked through in detail last lecture. Continuing on, we see that now we look at the left-hand side out only dims, and we come up with a candidate where the left-hand side is sharded, the right-hand input is replicated, and it produces a sharded output. And that corresponds with this very first example we talked about last time. Then we go with the right-hand side, and we come up with a candidate where the left hand is, the first input is replicated, the second input is sharded, and then the output is also sharded, and that corresponds to the second example we talked about. We have no linearity strategy here, but if we jump down, basically at this point, you can see that if we print out the strategies over one mesh dim, we have these 4 candidates, and these actually map 1-to-1 with the 4 candidates we talked about last lecture, which is nice. And here we do something interesting, which is we do a cross product across all of the mesh dimensions. This will just allow us to come up with placements where shards are actually across multiple mesh dimensions. In this case, we only have 1 mesh dimension, so it doesn't really matter, but just interesting to note. So now that we've come up with all of the strategies, the next step is to filter the strategies. So we come here, and for each strategy, we basically check if the strategy is shardable. And if we look in here, it basically will check if the shard dimension is greater than the length dimension, then it returns false. The intuition here is that, if you have 8 shards, but your dimension is only 5, then there's no way to shard across, your 8 ranks. If they both are, if they both pass, then we will add it to this filtered strategies list. But before we do that, we actually calculate the cost of the strategy. And it can be kind of interesting to look at this. So if we look at this generate redistribute costs, we go to redistribute costs, we can see that basically what it does is it takes our topology, our mesh topology, and it calculates all of the collective costs. So you can see this all gather, all reduce, etc. And then if we go into here, we can see that there's just some math that basically will estimate how expensive each of these collectives are. It will aggregate all of these costs together, and then it will assign this collective cost to the strategy. And then I'll add it to this filter strategies list. And then we set it to this MM strategy. So if we go back up the stack, at this point, op strategy has all of our candidates. Now we come here to the select strategy, and this will basically filter down from our 4 strategies or n strategies down to the best one. And if you look at the code, it basically takes a min. It basically figures out the minimum cost and then uses that to select the best strategy. Yeah, and if we go here, now this op info has this output sharding that we've just gone through the trouble of calculating. If the output sharding did need to redistribute the input tensors, it will. In this case, it actually will. And this is the reason why when we continue, we'll actually jump here, which might be confusing. And the reason why we jump here is because to do the redistribution, we actually issue a collective. And when we issue the collective, we wait. And so therefore, this other rank has now hit their breakpoint. But we'll just kind of disconnect and we'll continue down to see what happens next. Okay, so now after the collective operations are done, the input tensors are redistributed to their new placement types. We'll actually just very simply do the op call, which as you'll recall is just an atem mapmul on the local tensors. And then so now we'll have this local result, which down here we will rewrap this local result into a DTensor and return that. And now you have the output, which is a new DTensor of the mapmul, and you can continue down as you go through more and more operators. But hopefully this was a good overview of what's going on behind the scenes with DTensor. In the next lecture, I'm going to dive more into the redistribution code, in particular how redistribution handles things like backwards operations. But yeah, hopefully this was interesting, and I'll see you in the next lecture.